It's Mrs. Mafucci, and it's time to review solutions, a review for the Chemistry Star exam, and my comprehensive final. So you may want to go get your reference tables before you start watching this video. A solution is an example of homogeneous matter. It is made up of a single phase in which there is an even distribution of the individual components. Each substance retains its individual properties. A solution is made up of a solute. That's the substance found in the least amount which gets dissolved. And a solution is made up of a solvent, which does the dissolving. It's the substance found in greatest amount. Water is the universal solvent because it can dissolve so many substances. A solution in which water is the solvent is referred to as an aqueous solution. This last equation shows the dissolving of glucose. You can see that the dissolving of glucose is a physical change. Dissolving does not change the chemical composition of a substance. Glucose does not change into another compound when it dissolves. It only changes its physical state. It is going from glucose solid to aqueous glucose, which means it's dissolved in water. This is just a physical change. Ionic solids, or salts, contain positive and negative ions, which are held together by the strong force of attraction between particles with opposite charges. When one of these solids dissolves in water, the ions that form the solid are released into solution, where they become associated with the polar solvent molecules. In other words, when an ionic solute dissolves in water, it breaks up into the positive and negative ions that make up the solid. So, ionic compounds are a crystal made up of negative and positive ions that are held together by the attraction between oppositely charged ions. The water molecules are able to break that electrostatic attraction, and that allows the cations, positive ions, and the anions, the negative ions, to separate. When an ionic solid dissolves, water molecules surround the positive and negative ions. So you can see in this example that when salt dissolves in water, the water breaks the crystal lattice, allowing the sodium ions to separate from the chloride ions. This is how an ionic solid dissolves in water. A soluble salt will dissolve by completely dissociating into the positive and negative ions that make it up. Notice that I wrote the dissolving of salt with a single arrow. Do you see that? NaCl solid goes to Na plus Cl negative, a single arrow. No equilibrium is established because the equilibrium constant is so large, the reaction lies completely to the right. That means the sodium chloride solid completely breaks apart into the sodium ion and chloride ion. This is different if you're dissolving a slightly soluble salt. For example, looking at silver chloride. The dissolving of a slightly soluble salt is written as an equilibrium reaction. In this case, an equilibrium is established between the dissolving and recrystallizing of the solute. In this example, the silver chloride is in equilibrium with the silver ions and the chloride ions. But the K is so small, the equilibrium is so small that the reaction lies to the left, and this salt is not very soluble. The larger the K, or the KSP, the solubility product equilibrium constant, the larger the K, or KSP, The more the reaction lies to the right, and the more the products are formed, the more ions are formed, and the more soluble the salt is. Do you see the difference between NaCl and AgCl? The sugar we use to sweeten coffee or tea is a molecular solid in which the individual molecules are held together by relatively weak intermolecular forces. When sugar dissolves in water, the weak bonds between the individual sucrose molecules are broken, and these sucrose molecules are released into solution. Molecular solids or covalent molecules do not break up into ions when they dissolve in water. Instead, when a molecular solid dissolves in water, the bonds between the atoms are not broken, ions are not separated. Instead, the intermolecular forces of attraction between the molecules are broken and the substance dissolves. During the dissolving process, water molecules surround the individual molecules of the sample of matter. So take a look at this example. C12H22O11 solid does not break apart into carbon atoms, hydrogen atoms, or oxygen atoms, doesn't break apart into any kind of ion. It just stays as molecules, but the molecules become surrounded by the water. Now, some solids dissolve by releasing heat. This is an exothermic reaction. When a solute dissolves exothermically, the temperature of the surroundings increases. Sodium hydroxide is an example of a solute that dissolves in water in an exothermic process. When sodium hydroxide releases the energy when it dissolves, the temperature of the solution is going to increase. This is why if you touch a beaker that is dissolving sodium hydroxide in it, it's going to feel hot to the touch. Conversely, some solutes dissolve endothermically, which means that they absorb heat from the surrounding. As shown in this example, the heat is on the left side of the arrow, meaning it's endothermic. When ammonium chloride dissolves in water, it absorbs energy from its surroundings and the temperature goes down. And this is why if you touch a beaker that contains a solute, such as ammonium chloride dissolving in water, it's going to feel cold to the touch. Now, suppose I put a lifesaver in my mouth. How could I increase the rate at which the lifesaver disappears or dissolves? In other words, we're going to look at how can I change the rate of dissolving. Specifically, I want to know how I can speed up the rate at which something dissolves. Now, if I close my mouth, the temperature will increase inside my mouth. That is why you keep your mouth closed when you take your temperature. As temperature increases, the rate of dissolving increases for most solids. The next thing I could do is I could swish that lifesaver around in my mouth, thus increasing the contact between the lifesaver and my saliva. This is like increasing the contact of the solute with the solvent. This is almost like stirring a solute. As stirring or agitation of the solute increases, its contact with the solvent increases and the rate of dissolving increases. Another thing I could do would be to chew the lifesaver. If I chew it and broke it up into smaller and smaller pieces, that would increase the surface area. Again, increasing contact between solute and solvent. As the surface area of a solute increases, its contact with the solvent increases, and the rate of dissolving also increases. So, as temperature increases, the rate of dissolving increases. Now, the opposite is true for gases. If you increase stirring, you're going to increase the rate of dissolving. And lastly, as surface area increases, rate of dissolving increases. Now let's go to Table E of your reference tables, which gives you the relative solubilities of substances in water. Let's consider the table shown on the right, which is very similar to your Table E. Which aluminum salts are insoluble? So you want to find aluminum, and let's consider it. Look at aluminum. Do you see which two aluminum salts are insoluble? That would be aluminum hydroxide and aluminum phosphate. Which two metals form salts that are all soluble? So now you want to find your metals and see which ones form soluble compounds. Do you see that potassium and sodium, all of their compounds are soluble in water? Okay, the other one is ammonium. Now, ammonium is not a metal, but it is a positive ion. We're going to consider that potassium and sodium salts both form salts that are all soluble, and the ammonium ion also has salts that are all soluble. What are the products of the reaction between copper 2 chloride and silver nitrate? Now this is an example of a double displacement reaction where the copper and the silver are going to change places with each other. The two products of a double displacement reaction for this example are copper 2 nitrate and silver chloride. Did you see how I got that? The copper and the silver change places. Now in a double displacement reaction, usually one of the products forms an insoluble precipitate. Well, which one does? Is it going to be the copper nitrate or the silver chloride? Let's see. You can see that copper 2 nitrate is soluble, but silver chloride is insoluble. That means our precipitate will be silver chloride.